All right, so welcome to the last week of class. You can believe it. We're actually here at the last week of class for this quarter. So good Monday morning. So the plan pretty much for the rest of whatever today, after we go over any homework questions, we're going to look at what's called Newton's method, which is a way to find zeros of functions that uses calculus. Then on Wednesday, we're going to have our last quiz for the quarter. That quiz is going to cover sections 4.8 and 4.9. I'll mention this later. But 4.8 and 4.9, that's L'Hopital's rule, what we did at the end of last week, and Newton's method that we're going to talk about today. After the quiz on Wednesday, then we're going to talk about antiderivatives, which are exactly what they sound like. They're derivatives backwards. And then Friday will be a review day. We'll get ourselves all set up for the final, and the final exam is 1 week from today. So we will be done with calculus, Calc 1, Math 105, a week from today. So that's where we are. Can't believe that we're already at this point, but that's kind of cool. Anyway, so that's the plan going forward. But before we dive into it today, let me open up for any questions on homeworks or anything else we've been talking about. Anything out there we need to look at? All right, so Bailey just put in the chat he'd like to look at number 9 from 4.7. Any others? All right, so I'm going to go ahead and pull that up. We'll take a look at it. While I'm doing that, let me just ask, how's L'Hopital's rule treating you? How do you guys feel about that?
Okay.
Just okay. I'll take
I mean,
it.
it was easier. No, I liked it because it saved paper.
Okay.
It saved paper, so I didn't need to like waste half a page solving one problem, because sometimes the answer is in the problem.
Okay.
And I liked doing that on the homework, and I was like, oh wow, the answer is right in the problem. That's simple, or it's a 0.
Yeah, L'Hopital's rule can be really, really fast, which is nice. Saw some thumbs up. So, okay, good. I'm glad to hear that. Most people really like L'Hopital's rule, especially since it came right after, this applied optimization, these word problems. But it also made limits. It makes limits super easy, especially compared to what we had to do back in the day. All right. So let's hop down here and look at question number 9. All right. So Centerville is the headquarters of Greedy Cablevision Inc. Cable company is about to expand service in two nearby towns, Springfield and Shelbyville. There used to be cable connecting Centerville to both towns. The idea is to save on the cost of cable by arranging the cable in a Y-shaped configuration. Centerville is located at 12,0 in the XY plane, Springfield's at 0,7, and Shelbyville's at 0, -7. Cable runs from Centerville to some point x, 0 on the x-axis, where it splits into 2 branches, going to Springfield and Shelbyville. Find the location that will minimize the amount of cable between the 3 towns and compute the amount of cable needed. Okay. And then notice that it does have a couple of pieces to this question, right? So it says to solve this problem, we need to minimize the following function of x. We find that f of x has a critical number at blah, right? Verify f of x as minimum, compute the second derivative, find its value at the critical number. Right, so basically they're walking us through the steps. Find the thing we're optimizing, Find the critical numbers by differentiating, checking for 0 and undefined. Check the second derivative at that location to make sure that it is going to be a minimum, and then figure out what the minimum is. So let me go ahead and start by writing down these numbers just so that whiteboard. All right, so let me share whiteboard and let's see if we can figure this out. All right, so basically here's our picture. If we look at the XY grid, we are told that our cable company is located at 12-0. Okay, so somewhere out here is 12-0. All right, so then the two towns that we're looking for, Shelbyville and Springfield, I don't remember exactly which is which, so it doesn't really matter, but one of them is up here at 0.7, and the other one is at 0 - 7. And what our goal is, we're going to do our cable so that at some location on here on the x-axis, we're going to split it and go to those two spots. All right, and so this is going to be at x0. All right, so is everybody good with the picture and the setup? What we're trying to do here? All right, so what we're trying then, or what we need, is a function that shows the total length of these three pieces that depends on x. Okay, so let's start looking at the three different chunks, and let's actually look at this top part, the one that's going up to, let's call that one Springfield, the one that's up above. Okay, so if we were to look closely there, we'd see a triangle. Right, we've got our cable length over here. And here's what we know about this triangle. We know that this is length 7. And we actually know the bottom length, at least in terms of x. What would that be in terms of x? Yeah, it's just x, right? If that's the point x0, x is how far we are from the axis. So that means that this length up here, we can find that from the Pythagorean theorem. And so that's the square root of x squared plus 49. All right, so that's the length. I'm going to call that length number 1. Well, length number 2, by symmetry, is exactly the same, right? So if we're going to look at the total length, it's going to be the square root of x squared plus 49 plus another square root of x squared plus 49. But now we need to get length 3. So the question is, how long is length 3? Well, it's definitely not going to be 12. It's going to be less than 12 because we're not going all the way. So how long is it going to be? Can anyone give that to me in terms of x?
Just 12 minus x.
Yeah, beautiful. It's just 12 minus x, right? Because however close we got to the axis here, we take that away. All right, so here's actually the answer to the first part, where it says the function that we're trying to, what's the function that we're trying to minimize? That's not 99. 49. Okay, so we've got 2 square roots of x squared plus 49 plus 12 minus x. All right, so how are we doing at this point? Does that make sense? All right, so that's what we're trying to we're trying to optimize. So now let's differentiate. So if I differentiate that thing, for the first part, I need to use the chain rule. So it's going to be 2 times 1/2 x squared plus 49 to the minus 1/2 times 2x. So the 2 was a constant multiple, and then this came from the chain rule. And then plus 12, that gives me nothing, and then minus x gives me minus 1. So we've got f prime of x is equal to, looks like it's 2x over the square root of x squared plus 49 minus 1. So now we need to find critical points. All right, so critical points, we have to worry about where this is 0 or undefined. In terms of undefined, never happens. This denominator is never equal to 0 because x squared plus 49 is always at least 49. So it's never undefined, but we do have to worry about where it equals 0. So let's take a look at that. We're going to have 2x over the square root of x squared plus 49 minus 1 equals 0. Move that 1 over. Now I can cross multiply. Now I'll square both sides to get rid of my square root. It gives me 3x squared equals 49. X squared is 49 thirds. Or x is 7 over root 3. Or if you'd rather, 7 root 3 over 3. So there's our critical point. So that's what's going to go in our second box. All right, but now they did say, hey, let's go ahead and confirm that by looking at the second derivative. I'm not going to bother doing that. At this point, take a second derivative, plug in this number, see what you get. You will see that it is a positive number. So this thing is concave up, which means it's a min. And then if we want to know what goes into the last box, which is what is the actual length, well, we're going to take that 7 root 3 over 3, put that back into here for f. Again, I'm way too lazy to do that. All right, so is that at least better for this one, Bailey? You see where you need to go with this?
Wait, you put the critical point back in the which function?
My length,
Okay.
right? Because isn't that what they asked for? What's the total length needed for this minimum? At least that's what I recall it asked. So it really depends which box we're doing, right? Where we plug it in. So once we get that number, if we want to check concavity, we plug this into the second derivative. If we want the actual function value, we plug this into the original function. All right, so good for that. All right, any other homework questions before we dive into Newton's method? No? All right, cool. Well, then what I'm going to do is hop up to the whiteboard. So just give me 1 second and I'll be right back with you. All right. So last time, which was forever ago, we saw L'Hopital's rule. Great application of derivatives, allows us to evaluate limits very quickly when they're of the right form, 0 over 0 or infinity over infinity. The only trick we ever had to pull was to get it into one of those forms. But once we had it, L'Hopital's rule was awesome, right? Differentiate top and bottom separately, keep that fraction, do the limit again, right? And keep doing it until you stop getting indeterminate form, and you'll eventually get your limit value. So that was pretty cool, right? Well, the application of derivatives I'm going to show you today actually helps us with another problem that we had to do back in the day, actually even in pre-calculus, which is finding zeros of functions. So let me just kind of remind you what I'm talking about there before I dive into this thing called Newton's method. Okay, so what this means. So finding a zero of a function. So this was back in the good old days when we had some sort of a function that, I don't know, did whatever. Let's say we got a polynomial that does something like this. The zeros of this function, these are places where f of x equals 0. And on a graph, that means x-intercepts. All right, so when we found a zero of a function, it was where the function equals 0, also known as an x-intercept. So anytime that you've been asked to find x-intercepts, you've been finding zeros of function. And so we know what to do. We take the function, we set it equal to 0, and we solve it. But the problem is sometimes that's not so easy, right? Sometimes it's not so easy to actually take a function and set it equal to 0 and solve. The setting equal to 0, yeah, that's no big deal, but the solving can be impossible. If it's something easy like a quadratic or anything like that, or something that factors, something with a square root, we know how to attack those problems, right? But the question is, what if we don't have that? All right, so this is where this new topic comes in, this thing called Newton's method. So Newton's method is named after Sir Isaac Newton, right? One of the inventors of calculus, because he was the first one to come up with the idea of Newton's method. All right, so let me kind of show you how Newton's method plays out with a graph, and then we'll kind of build how we do this. All right, so here was Newton's idea. Let's come back to this function, and let's say we are trying to find this 0 that's at the very right. Okay. Now, it's unlikely that we're going to be able to guess this number exactly. Okay, but let's say we can get kind of close. So instead of going with this value, let's say that we make a guess of this x. All right, so this is going to be our guess for the 0. Now, it clearly doesn't give us 0, right? You can see that the point here on the graph is not an intercept. And so that means that our guess isn't good. But here was Newton's idea. Newton said, well, you know what? What if we take the tangent line at this point and find its intercept? Okay, so I'm going to draw the tangent line at this point. And let's look at its intercept. So its intercept, try to use a different colored dot. Maybe you can see a slightly different color, not really. All right, well, its intercept is over here. So you'll notice that those 2 points aren't the same, but the one on the line is actually pretty close to the actual 0. Okay, so big surprise. Newton's using the line, the tangent line, to approximate the curve. I mean, isn't that kind of the whole point of calculus anyway? All right, so, but here's what Newton saw. He saw, well, look at that. You see our first guess was, a little bit a ways from off from our actual value. Well, where the line brought us is actually closer to the true value. So then here was Newton's thought, what if we just did that again? What if we took this new point and we ran up on the function there and did it again? Find a tangent line. Find its zero. That should be a closer guess. Do it again. Do it again, do it again, do it again, do it again, do it again. So that's entirely the idea behind Newton's method, is just this, well, keep making guesses until you get sufficiently close to the actual zero. All right, so this is the idea behind Newton's method. Use that tangent line as an approximation for the function, find its intercept, and use that as our next guess. All right, so let me write that out in words. All right, so we just start with a guess, make a guess for the zero. And you gotta love a method that starts this way. Make a guess. Well, how do you make the guess? Make a guess. What do you think? What's kind of close? It looks like it's around a half. Okay, cool. Go with a guess of 1/2. It looks like it's around 13. Okay, cool. Plug in 13. Right? It doesn't matter. There are going to be certain guesses that don't work for us. I'll talk about that. But in general, no, we just make a guess. Right? So make a guess for the zero. So then what we're going to do is we're going to find the tangent line. At this guess. We've done a ton of this. You find the slope of the tangent line using the derivative. You get the equation of the tangent line using the point. Right? So we've done a ton of this. So you find that tangent line. Then find the zero of the line. And this is actually really easy. If you have an equation of a line and you set it equal to 0, easy to solve. Okay, so we find the zero of that line. So then we use this as our new guess. And then repeat the process. So we take that next point, try it again. So find the equation of the tangent line, or find the tangent line at that new point. Find it 0. Use that as the next guess. And then again, and again, and again, and again, and again. So this is what we call an iterative process. It just repeats, goes over and over and over and over. But basically it's make your guess, find the tangent line, find it 0, use that new guess, repeat. Okay, so this is the idea behind Newton's method. Now, I am going to help you out because this is the same process every time. Think like a mathematician. Mathematicians, we don't like doing it every single time. We want to do it once generically. So let's do this generically. Let's take a generic function. Let's find that generic tangent line. Let's find its generic 0. And if we do that, we're going to get a nice little formula that we're always going to be able to use. Okay, but before I dive into that, are we cool with the idea, what we're trying to do? Any questions? Cool. Thumbs up. All right. Awesome. Seeing some thumbs up. I like that. All right. So here we go. Let's just start with a line. And let's find the 0 of a line. Okay. So let's do that generically first. All right, so let's just start with a line, and I'm going to start with it in the y minus y naught equals m times x minus x naught. Okay, because this is the form we're going to be using. We're going to get a slope, right? We get the slope from the derivative, and we're going to have a point from our guess. So this is the form we're going to use. That's why I want to start here. So here is a line. Now, if we want the 0, basically what we want to do is we want to set y equals 0 and solve for x. Right? That's what it means when we find a 0. So let's do this generically and let's see what happens. So if y is equal to 0, we get minus y naught equals m times x minus x naught. So I'm going to divide by m. So I get minus y naught over m equals x minus x naught. And then the last thing I need to do is add that x naught. So I get x equals x naught minus y naught over m. All right, so basically what this formula tells you is if you know a point and you know the slope, so if you know the slope and a point for your line, this is how you find the 0. Just plug it. Okay, so that's just finding the 0 of a line. Now let's talk about finding the 0 of the tangent line. All right, so what I'm going to do is let's think about this. Let me rename some things. For our initial guess, I'm going to use x sub I, little subscript I, meaning it's my initial guess. Right, I for initial. Okay, so that means then the point is going to be x sub I, comma, f of x sub I. We're going to get the point for this tangent line by plugging that number in. Right, we'll get the y by plugging it into the function. And then the slope, that's going to equal the derivative evaluated at x sub I. All right, well, let me put all this stuff in here then. We're going to get x is equal to x sub I minus f of x sub I over f prime of x sub I. And I want you to put a box around this, because this is the important part of Newton's method. Because this right here is our formula for getting our next guess, our next better approximation for the 0. All right, so you're going to start with whatever your initial guess is, plug it into this formula, get a new guess. Then you're going to take that number, plug it into this formula, then plug that new number in, then that new number in, again and again and again and again and again and again and again. All right, so here is the process. It's actually really easy because it's always set up exactly the same way. And you always just start with your best guess, and see what happens. All right, so let's try it out. Let's see how this works. Let's take a function and see if we can find the 0. Now, this is going to require technology. Okay, we are going to need a calculator, computer, or something like that to run these numbers. Need to is a strong word. Unless you want to deal with horrible, nasty fractions, you need a calculator. So I'm going to be doing that. I got my TI-89 handy here and ready to go. All right. But just realize that this is something that, this is a process that actually gets programmed into computers. A lot of computers, when they solve things, they use Newton's method or a variation of it. So just realize this is going to be technology based. All right, so let's start with something pretty easy. This is a function that we can find the exact zeros for, but I'm going to want a decimal approximation for this number. So let's see if we can find the zeros of f of x equals x squared plus x minus 1. All right, so like I said, this is a function that we know pretty well. What kind of shape is it?
Parabola, because of the square.
Okay, it's a parabola. Is it happy or sad?
It's
Is it a
happy.
smile or a frown? Yeah, it's a happy. So it's a smile, right? We know its y-intercept is at 0, -1. We could find the vertex by doing the whole negative b over 2a thing, right? So like we could actually get a good graph of it. We know everything about it. If we actually wanted to find the zeros, we set it equal to 0, we could use the quadratic formula. But let me show you how Newton's method would work to find those zeros. Okay, so what this thing looks like, we're going to draw the graph of it. Looks something like this. The vertex is at -1/2. There's our intercept at 0, -1, and it's a smile. Okay, so I know I said find zeros of this. Let's just find one of them. Let's just find one of the zeros. And then you can see you could use the same process to find the other one. So let's find the positive one. Let's find the one that's out here. All right, so think about what we need for Newton's method. We need the function. Yeah, we got that. We also need its derivative. All right, well, let's get its derivative real quick. Derivative is fast and easy. F prime here is going to be 2x plus 1. All right, so let's use this formula to figure out what our next number is going to be. All right, so we're going to take x and we're going to subtract from it f of x over f prime of x. So I dropped the little i's off of it just because I'm lazy. But notice that so that's our x minus f over f prime. And in fact, let's just go ahead and get a common denominator for this. Just because it'll be a little bit easier when it comes time to doing the calculations. So I'm going to get 2x squared minus x squared, which is 1x squared, I'm going to get x minus x, which is 0. A minus negative 1 is plus 1. So a little bit of algebra on that. Tells us what our next one is going to be, or how we're going to get our next value. All right, so I'm going to erase this. I just need a little space. Hopefully everybody's got that written down. Okay, but this is our new estimate. It's going to equal x squared plus 1 over 2x plus 1. Okay, so now we have to make a guess. We have to make a guess for a value for the 0. So anybody have a nice number you want to plug in here as a guess for that root, for that 0?
Can we plug in 0?
We can plug in 0. That could be our, I mean, if we plugged in 0, that's a, well, we're actually going to be using the tangent line at this point. I think that would totally work. Because if we're here, we get its tangent line. That brings us into this point. Okay, well, if we run the function, find its tangent line, it's going to bring us into this point and eventually get us closer and closer and closer. So I think 0 totally works.
Okay.
If you don't want to use 0, you could use 1, you use a half. I guess you could use 100, but 100 is probably not a very good guess.
Well, I don't like fractions. That's why.
Okay. Well, I'm with you. I don't really like fractions either. However, we're eventually going to run into fractions.
Yeah, I know. I was realizing that when you drew the graph, I was like, oh, it's going to be more of a fraction if we started half.
So, but 0 sounds totally cool.
Okay.
All right, so let's see how this plays out then. So here's going to be our first guess. Now, the way I'm going to label these, so I just wrote here x sub 1, meaning this is our first x. Now, I am going to warn you, I don't know because I haven't looked at the book. Some start with x sub 0 as your first guess. I like starting with x sub 1. That's my first guess. All right. So the question then is, what does x sub 2 equal? All right, well, let's plug that in. So x2 is going to equal 0 squared plus 1 over 2 times 0 plus 1, which is 1 over 1 or 1. So if we start with a guess of 0, Newton's method says, okay, the next better guess is actually 1. So like on my picture, that would be this value right here. This is x equals 1. All right, well, let's figure out what x3 is going to be. x3, now what we're going to do is we're going to plug 1 into there. So I'm going to get 1 squared plus 1 over 2 times 1 plus 1, which is 2/3. All right, so Newton's method now brings us back in to 2/3. Well, let's get a next better guess. Now we're going to take 2/3 and we're going to plug it in here. So we're going to get 2/3 squared plus 1 over 2 times 2/3 plus 1. So notice that every time this form is identical, the only thing that's changing is what we're plugging in. And what we're plugging in is the number that we got from the step before. Okay, well, let's see. So 2/3 squared is 4/9 plus 1 is 13/9. 13/9 divided by, let's see, 2 times 2/3 is 4/3 plus 1 is 7/3. So if I do the old flip and multiply thing, I'm pretty sure I get 13/21. Okay, so that's my next better guess. Let's get a decimal approximation for that. Because at this point, you're starting to not really get a feel for what 13/21 is, right? Like, you know what 2/3 is, 0.6 repeating. So this is 0.619, 0.619. There's some other stuff around it. Okay, well, I'm going to get one more. I'm going to go to x5. Now, x5 can be found exactly the same way. It's just in this case, we're going to plug in 13/21. So x5 is going to equal 13/21 squared plus 1 over 2 times 13/21 plus 1. I am most definitely not going to worry about the decimals on that, or the I'm not going to do the fraction stuff on that. But let me just see what we get here. So 13 divided by 21 squared plus 1 divided by 2 times 13 divided by 21 plus 1. So as a fraction, just because if you're curious, x5 is 610/987, obviously. But as a decimal, that's around 0.618. Okay, so I just want you to look at what's happened now. So we started with a guess of 0, which was a fine start, but definitely not where that root is, not where that intercept is. That jumped us to a guess of 1. The guess of 1 brought us to 2/3, so 0.6666666, which brought us to 0.619, which brought us to 0.618. And I want you to notice what's going on. Notice that those x's are starting to kind of settle down, right? We're getting to the point where we're starting to not change that much. And that's a good sign. That means that we're getting actually pretty close to the 0. So if we were to do this one more time, if we were to take this value and put it in, let's see what we get. So I can do this pretty quickly on my calculator here. Okay, so x5 was 0.618. I'm going to give you a couple more decimals just because I want you to see how little of a change there is once we're at this point. So 618.034447822. Okay, so that's as many decimals as my calculator gives. If we now plug this in to the formula, we get 0.61803398875.
So what's the point if we continue this then? If you keep getting like the first 3 digits the same? Like, because wouldn't it be faster if you like put it into like a system than doing it by hand? I mean, I guess by hand you have more chances of accuracy.
Okay, so I don't know if I quite catch your question, or I don't think I caught that question.
So like, why would you have to continue on? Like, I don't know what x number you're going to stop at, but like after like what point of it repeating itself, like the first 3 decimals, like 618 in our case, like at what point do you know you should stop?
Okay, Now, so the answer to that question, you're going to love the answer to that question. It depends. It depends how accurate do you want your zero? How many decimal places do you need? Like for me at this point, I mean, please check this out. The difference between these two, right? We already are repeated the first 5 decimal positions, right? Which means we're off by, what is this, 10, 100,000, 10, 100, we're good to the millionths spot. For just about anything, that's precise enough. But if you wanted more precision, you would do it again. Well, let me just do it again real quick. And just so you know, I got exactly the same number for X7 on my calculator.
Oh, that's relieving.
Meaning that we're at least good out to this decimal spot. If we need more decimals, we'd have to have something a little bit better than even my handheld calculator here. So basically, you're going to keep going until you get as many decimals fixed as you want. Right?
Okay.
What I tend to do is I go as far as it requires my calculator to spit out the same answer. And then I know that I'm good at least that many digits, which on mine, I mean, what are we talking? That's like 12 digits or something. Yeah, that's our root. So Newton's method works really, really well. It gets you there very quickly. I mean, look at it. We were after just a few guesses, like the first time we actually needed to use our calculator to approximate this decimal, we were already within 1/1000th, which is pretty darn good, right? So you can actually get there very quickly. In general, the closer you are with your initial guess, the faster Newton's method brings you to that point, right? So if we hadn't started with a guess of 0, if instead we had started with a guess of like a half, we probably would have gotten there a little bit faster. But I was totally cool with starting with 0 because, yeah, this is our first one. We're not in a race or anything. And so instead of getting there at x = 6, or on the 6th one, we get there on the 4th one. Yeah, whatever, it doesn't matter. All right. But this is the idea. And it's actually really, really simple idea. Always using that same form. Right. So if you were to do the quadratic formula on this, right? I mean, this was a quadratic. We could have done the quadratic formula. Let me just show you really quickly. The actual 0 is -1 plus or minus the square root of 1 plus 4 over 2. So -1 plus or minus √5/2. Well, this number right here that we found is the decimal approximation for -1 plus √5/2. Take your calculator, get the decimal approximation for that, and you'll see that it's 0.61803398875. By the way, if you've ever wondered how your calculator magically knows the square root of 5, gives you all those decimals, it's because of stuff like this. It's because of stuff like Newton's method. It gets programmed. It's a really easy program. I don't know if any of you guys are programmers, but just like the pseudo code for this is really easy. Here's a function. Find its derivative. Put it into this form. Right? Plug in your initial guess. Repeat. Right? It's an easy kind of loop that you would do, and you'd say keep doing it until you're good within so many decimal places. All right, so here's your process. It really is this straightforward. So let's do another one. Let's do a function that's a little bit more complicated, but you're going to see that the process doesn't really change. But before I do that, any questions on this one? All right, I'm going to assume everything is all good then. All right, so let's take a function that's a little bit more complicated, whose root may not be terribly obvious. So let's try this. Let's go, we're going to stick with polynomial, but let's make it a little bit bigger degree. So let's go with f of x equals 5x to the fourth minus 3x squared plus 2x plus 1.
Did we take the derivative then?
Okay, so here's the function. Again, we're going to try to find the zeros of this function. Actually, you know what? Let's make this a -1. I just want to ensure that we've got zeros. I'm not 100% certain that if it's a plus, it does. I think it does, but this one I know for sure does. All right, so let's think about what Newton's method needs us to do. Let me go ahead and put it back. I'm going to put it back up on the top here. So for Newton's method, here's another way you're going to see it. And I think this is probably what the book shows you. So I put the little subscript back on there. But you'll notice that over here, these are n's, and the next ones are n plus 1. Just the n plus 1 means that's your next guy, right? But it's always the guess minus the function at the guess divided by the derivative at the guess. So I think that was Susanna who chimed in there. We need to take the derivative with a question mark. And the answer to that is absolutely, because that's part of our formula. So let's take the derivative. So that's going to give us 20x cubed minus 6x plus 2. So for Newton's method then, we're going to have our function. Let me strip off the sub-ends just to keep it from getting too cluttered here. All right, so there is the formula that we're going to use. Like before, we can get a common denominator if we want, but I'm not going to bother. I'm just going to leave it like this. But this is what we're going to plug in our guess. This is what we're going to take our guess and plug in. And then once we get the new number, we'll plug it back into this. And take that new number and plug it back in, plug it back in, plug it back in. All right, so this is cool. We got our formula. So the next thing we have to do is start with a guess. We need to make a guess for a root or for a zero. All right, so in order to do this, let's actually draw a graph of this function just so that you can see it. Because I think that will help us a little bit when it comes time for us to find a zero. So let me go ahead and share my screen here. Okay, so everybody should be able to see Desmos now, hopefully. All right, so let's go ahead and type in this function, see what this looks like. So we have 5x to the fourth minus 3x squared plus 2x minus 1. Okay, so you can see on this graph, it looks like there are 2 roots. And let's go ahead again, try to find the one that's, this time let's go find the one that's on the left. Let's find the one that's over here. Okay, so looking at that, what's a good guess for that 0? Approximately what? All right, so Mariola just put in the chat box -1. I think that's great. So let's do that. Let's go with our initial guess of -1. Okay, so x1 is going to equal -1. So I'm going to make a list here. x2, x3, x4. So we'll see what we actually find those to be. So let me stop sharing for a second here so you can see the whiteboard again. And let's actually do this calculation. Okay, now I'm going to show you a trick for the TI-89. You can do something similar for most scientific calculators. You can probably also set up computers to do this depending upon what kind of computer calculator you're using. But here's how I'm going to do this. So if you've got a calculator that will take the last answer, the last thing that you calculated, and allow you to plug that in, this is a great trick. So here's what I'm going to do. I'm going to start by just typing in my initial guess. So let's see if we can get this so you guys can see it. Probably not. I don't think it focuses in on it. Anyway, I'm just going to hit -1 and hit enter. So all I did was I just typed in -1. Now what I'm going to do is I'm going to enter this formula. And everywhere there's an x, I'm going to use ANS, A-N-S. And it's down here on the minus button. It's a secondary function. So I'm going to do second minus, and that gives me ANS. What it actually shows on my calculator, I don't know if you can see it, negative. It says ANS and then 1 in parentheses. All right, so then I'm going to subtract, and then I'm going to put in there 5, answer to the 4th, minus 3, answer squared, plus 2, answer, minus 1, and then divide that by 20, answer cubed, minus 6, answer, plus 2. All right, so what my calculator gave me is my second guess, and if you don't want to use my little trick, that's totally cool. Just type it in, it works. You get -1.0833333, and so on. So our initial guess was -1. It didn't change much to get my x2. Now, if you do this trick where you type it in with the ants, all you got to do now is hit enter. And what it's going to do is take this number and plug it in. And so I got -1.07155920963. We are close. I know we're close because it didn't change much as I went from x2 to x3. Okay, so I just did it one more time to get my x4. -1.0712854.081. So check out how fast that was. We're already good to 3 decimal places in terms of this decimal approximation. All right, just for the hell of it, I did it one more time. X5 is negative 1.07128526226. And this time we're good to 6 decimal places. All right, well, there you go. There is the approximate value for that root. And I don't know if you remember, but on Desmos, and I'll show it to you again here in a second, but on Desmos, it actually gave me the decimals for that intercept. We'll see how it compares to the minus 1.07128526226. All right, so that brought us to that one. If we wanted to get to the other one, we would have started with a different initial guess. And I think that one over there was around like a half or something. So I probably would have started with 1/2. All right, so kind of cool. Kind of neat how fast it gets us to that value. So let me share Desmos again real quick. All right, so now you can see when I put my cursor over that point, you know, so it says it's negative 1.071. Yep, I agree. That's definitely how that thing starts. So we actually had those 3 decimal spots by the time we got to our 3rd guess. It was actually really fast to bring us into that point. All right, so good. Good for that one. All right. So I'm going to go ahead and stop sharing then. But I do need to talk a little bit about some drawbacks to Newton's method. Because Newton's method isn't perfect. There are definitely issues with this thing that we need to discuss. All right. And this is actually really easy. I can show you a specific problem with a simple function. But these are some things that we need to worry about. So, for example, let's say that we were looking at f of x equals x cubed plus x squared plus 1. So super easy, no big deal. And again, let's find zeros. And we're not going to draw the graph. Okay, I'm not going to actually draw the graph for you here. I'm going to show you another way that we could actually make a guess for an initial starting point. All right, so for example, let's just plug in 0. What do you get if you plug in 0 into this function? You're going to get 0 cubed plus 0 squared plus 1, which is 1. Right? Let's plug in another number. So I'm going to plug in a negative number. Like let's plug in, say, -2. You're going to get -8 plus 4 plus 1, which is -3. So I know that there is a 0 somewhere between 0 and -2. How do I know that? What in calculus tells me I know that. There's a specific theorem we saw once upon a time. Not the squeeze theorem, but I like where you're thinking there, Eris. There you go. Bailey just put the IVT, the intermediate value theorem. Yeah, intermediate value theorem. That was the one that said if we have a continuous function and we have whatever y values at the endpoints, every y value in between shows up somewhere. So since I know I've got a positive at one end and a negative on the other, and this is a continuous function, it's polynomial, I know I get every number between 1 and -3 somewhere between these two numbers, including 0. Okay, so I know that there's one somewhere in there. Okay, so cool. Well, let's choose an initial guess to try to find it. All right, so how about 0? That sound good? I mean, it gives us something that's not far from 0, plus it's really easy number to plug in later. So let's try 0. Okay, so we're going to do our initial guess of 0. So then let's figure out what x2 is, what x3 is, and so on. All right, so to do Newton's method, we need the derivative. So f prime of x is 3x squared plus 2x. Okay, so that means that our next best guess will be x minus x cubed plus x squared plus 1 over 3x squared plus 2x. Okay, so x2 then is going to be 0 minus 0 cubed plus 0 squared plus 1 over 3 times 0 squared plus 2 times 0. And do y'all see the problem? What's happening here that's an issue?
Dividing by 0.
Yeah, I'm dividing by 0. This is 0 minus 1 over 0. And the alarm bell should go off. Because what this means is there is no x2. And there is no next guess. What? Okay, well, here's what happened. Take a look at the derivative. Specifically at 0, what's the derivative at 0? Right, it's 0. What does that mean in terms of the tangent line?
It's also 0.
It's not 0.
I mean, it crosses the x-intercept.
No, that's actually not correct. What does the derivative tell you about the tangent line?
How close it is.
It's the slope, right? So this says that the tangent line has a slope of 0. What kind of lines have 0 slope?
Asymptotes?
You're way overthinking it.
Horizontal line.
They're horizontal, right? So if we have a slope of 0, we've got a horizontal tangent line. Now remember what Newton's method is doing. is it's saying, hey, take that tangent line and find its intercepts. Well, what kind of x-intercepts does a horizontal line have?
It don't.
The answer is none, right? They don't. So here is one of the problems, one of the things that can happen with Newton's method, is that your initial guess, like in this case, it was our initial guess, or a subsequent guess could actually bring you to a place where you have a horizontal tangent line. If that occurs, Newton's method's going to fail. Okay, so I'm going to make a list here of when Newton's method fails, because it does. That pen is dead. Okay, so here's the first place, is that your guess brings you to a point with a horizontal tangent line. So if that happens, Newton's method is going to fail. And that's what occurred here. X equals 0, that initial guess, gives horizontal tangent line. All right, so we got to watch out for that. Now, what would we do? Like, obviously, plugging in 0 is a problem. Could we still apply Newton's method to this to find that 0?
Yeah, just use a new initial number.
It's that easy. It's like, yeah, just choose something else. So you know what? Instead of 0, how about we try plugging in -1? Right? -1 is somewhere in there. We should expect that the 0 is going to be kind of close to -1. Try -1. If we started with an initial guess of -1, this is going to work out. It'll bring you into the 0. Okay, so if you ever run into this, where you get a horizontal tangent line, pick a different starting point. Change your initial guess. That solves it almost every time. Okay, so this is one place where Newton's method fails. Now, there are some other places that you can run into issues with Newton's method. This next one, let me just draw a picture for you. But suppose that we have a function that looks something like this. Now, obviously, I know it's really easy to see what the 0 is because it's 0, but just change your y-axis to somewhere else and you see that it's maybe not so straightforward. But let's say we started with an initial guess here of this point. So this is going to be x1. So x1 tells us to come over here, right? We follow that tangent line, brings us over to x2. Okay, well, x2 is this point. We do its tangent line. And it brings us back to x1. So we put that in, brings us back to x2, x1, x2. So here's another place where this is going to fail. And this is where we get into a loop, right? And I'm just going to put here, you cycle through a set of values. Meaning you just get into this loop. Usually it's a set of 2. You just keep bouncing back and forth between the 2 numbers, but there could be more, right? It could be x1 brings you to x2, which brings you to x3, which then brings you back to x1 or whatever. But you can sometimes get into this, well, we just keep cycling through a bunch of different values. All right, so your option here again is to choose another starting point. But there are some functions, like this one specifically, that you're going to run into this issue where you're just going to keep bouncing back and forth between values. And so sometimes it just fails. But this is another place where Newton's method will fail you. You just end up going back and forth, back and forth, back and forth between some specific value. All right, so there's another issue. There's a third issue that can happen. Let me draw another picture. Yeah, let's see if I can draw a picture for this. It's actually kind of similar to the one I've got drawn. Let's see, for this to do what I needed to, actually, I think I need it to be flatter. All right, so let's start with an initial guess. And we're going to be nice and close. I'll call that x1. So x1, we run up here, we use the tangent line. That brings us here to x2. I come out to this point, I draw its tangent line. Brings me to this guy, x3. All right, I run up there, I use its tangent line. Brings me out here to x4. All right, so what's going on now?
It's not a very linear pattern. It's like jumbled from, you go from positive to like more negative, and then back to more positive, and then back to more negative.
It's definitely the issue that we're getting further and further away, right? Like, think about my initial guess. I was awfully close to where I wanted to be. And each subsequent guess got brought further and further away. So that's the other time that Newton's method will fail, is that your guesses get worse. They move further and further away from the actual zero. Okay, now this is another situation where it doesn't really matter what your initial guess is, right? If I change that x1, I'm still going to diverge away from the actual value. It just might happen faster or sooner, right? So just realize that Newton's method isn't perfect. There are times when it fails. The one that you definitely can control is the horizontal tangent line. And fix that by changing your initial guess. 9 times out of 10, probably even more than that, it's going to work out. All right, so here's Newton's method. It's just another application of derivatives. It was a way, and is still a way, that we program technology to find zeros of functions. It lets us calculate things like the square root of 5 on our calculator. All right. Okay, so just a reminder, homework. There are 2 homework sets due tonight at midnight, the set on optimization and the set on L'Hopital's rule, so make sure you get in there and work on those. We are also going to have our quiz next time, our last quiz of the quarter. Again, it's going to be on the sections on L'Hopital's rule and Newton's method. Okay, so make sure you practice a little bit with Newton's method, but whatever I give you on the quiz should be pretty straightforward for that. So that's going to be coming up on Wednesday. All right, so other than that, any other last minute questions before we call it a day? No? All right, well, then everyone have an awesome couple days, and I will see you on Wednesday. Have a great day.